Our main application for now to higher order derivatives is to physics. We will in chapter 3 talk about the meaning of the second derivative in the context of a graph and also the first derivative a little more in depth. But for now, we're going to visit a more kind of intuitive example related to physics. So we've been talking about the first, second, third, fourth, fifth, thousandth derivative. And in physics, these have specific names. So we start with an original function. And in the context, this is all going to rely on the fact that our original function is what's called a position function or a distance function. It might measure distance from a starting point. It might measure height above the ground. Anything that tells you the location of an object from a particular point is called a position function. We normally use s of t to notate the position function. I don't know why s, but it normally is. Or in the context of something that represents height as distance, we might use h of t. In the next column here, I'm going to remind you of what the units might be for some of these. So just for sake of an example, say that your position function or distance function is measured in feet. If we find the first derivative of a function that measures distance, we get what is called the velocity function. I know that we talked about in section 2.3 that instantaneous velocity is found by finding the derivative of a position function and then plugging in a time. That is true, still true. It's just now we're calling this like whole thing just the velocity function. So v of t is what we'll call velocity, and that's the derivative, the first derivative of position. The second derivative of position, or the derivative of the velocity function, is the rate of change of velocity, and that is acceleration. It's how much, like how your speed is changing. So it's called the acceleration function. The derivative of velocity is acceleration, and we notate that by little a of t. So you could view it as the derivative of velocity, or it's the second derivative of position. Oh, it looks like, sorry, we forgot about the units. So the derivative of position, if the input little t is measuring time, say in seconds, the velocity, of course, will be feet per second. I know we talked about this a little bit ago. Then the acceleration will be feet per second, and so that's measured in feet per second squared. So this was something that we've seen before. The third derivative, though, is something that's new. And the third derivative, or the first derivative of acceleration, or the second derivative of velocity, the third derivative of position, this is what's called the jerk function. I don't really know why exactly it's called the jerk function. The only thing that might make sense to me is that if the derivative of acceleration would tell you how your acceleration is changing, and if it maybe changes abruptly, if you your acceleration just and you start slowing down really quickly, or you slam on the brakes, then that you get jerked around. I don't know. So anyway, we call this little j of t. It could be thought of as the derivative of acceleration. It would be the second derivative of velocity, or it would be the third derivative of position. And this would just continue on in this trend. This would be feet per second squared per second. So this would be feet per second cubed. So here's one example. Always shooting rocks or balls off tops of buildings or towers. So here's another example with that, mostly because the model tends to be pretty simple. And, this isn't a physics class, so we just want to keep it relatively simple. So here's the example. We're shooting a rock upwards from the top of a tower. The height of the rock in feet above the ground after t seconds from shooting it is modeled by h of t equals negative 16 t squared plus 144 t plus 160. Part A says find the height, velocity, acceleration, and jerk after 1 second. Part B says find the velocity with which the rock strikes the ground. And part C says find the maximum height the rock reaches. Okay, so for part A, finding height, velocity, acceleration, and jerk all at 1 second. So we're just kind of analyzing what's going on after it's been in the air for 1 second. So let's get started. We've got to just know our derivatives. So the height is just going to be h of 1, right? So there's no derivative there. So if h of t is negative 16 t squared plus 144 t plus 160, if we plug a 1 in for t, then that will just give us the height of the rock after 1 second. So when you calculate this out, it turns out to be 288 feet. Again, this is height at 1 second. Okay, so that one was easy. Velocity. Velocity at 1 second. So the velocity is the derivative of height. So we'll say v of t equals h prime of t. So to find the velocity, we're just going to differentiate height. So that'll be negative 32t plus 144. Okay, let's plug in 1 for t because we want the velocity at 1 second. Negative 32 times 1 plus 144, that's 122 feet per second. So this is the velocity at 1 second. Okay, so the 288 feet is how high it is. If you take a look at this function here, when you plug in 0, these two terms go away and you get 160 feet. So the tower or the rock starts at 160 feet. After 1 second, it's shot upward. So at 1 second, it's all the way up at 288 feet. And then this velocity is saying that it's moving upward still at 288 feet because the velocity is positive. So velocity always has a direction, up and down. Positive velocity means up, negative velocity means down, or maybe you're talking about forward and backward or left and right. So what this means here is that the rock is moving upward still. Right, there's another point in time where the rock will reach 288 feet again, because it's going to go up and then come down. So it's at 288 maybe here, it goes up further, and then over here it's at 288 feet, but that will have a negative velocity because it'll be going downward. Okay, so these two things together tell us how high it is, but also where it's going next, how the height is changing at that time. Sorry, I always circle stuff and then it lags a little bit. So these two things together, right, paint a better picture than just this one, which is really cool. I mean, intuitively, it makes sense that the rock's going upward maybe at 1 second, but you never know. So we found velocity. Now acceleration is going to be the derivative of velocity, or the second derivative of height. So we'll take our velocity function here and find its derivative. The derivative of negative 32t is negative 32. Okay, When we plug in a 1, we just get -32. The acceleration is measured in feet per second squared. So this means, so again, this is just the acceleration at 1 second. So this is always a constant function because when you have something that's basically not being acted on except in the beginning where the rock is shot upward, then the only thing that's changing the acceleration is the acceleration due to gravity. So no matter what we plugged in here, it would be constant at -32, and that is actually a constant from physics with the acceleration due to gravity. I think we also want to find the jerk. Yes, we do. Okay, so that'll be the third derivative. So j of t will be the derivative of acceleration. Okay, the derivative of -32 is 0. If we plug in 1, that's just 0. The units for that are feet per second cubed. All right, so this is the jerk at 1 second. The reason I think that the jerk is 0 is because, again, there's nothing that's, like abruptly acting on the rock for it to be jerked around. So there's nothing changing with that. And so it's just, 0. If we had a situation like that, the model would be pretty different. So when you have something with this motion, projectile motion, it always kind of works out in this way. So for part B, we want to know the velocity with which the rock strikes the ground. Okay, so we want to know a velocity at a particular point in time, at a particular one single moment in time, which is when the rock strikes the ground. So this is an instantaneous velocity, not an average velocity. We do need the time, though, when the rock hits the ground. So we went over an example with this in section 2.3. The way to go about that is to find when the height is 0. Okay, so the idea with this is the rock strikes the ground when the height is 0. Okay, well, we have a function that models height, or that gives us height at any time. So here we know the height, and we want to set it equal to 0, and we want to solve for t. So we've got a function is -16 t squared plus 144t plus 160, and we want to set this whole thing equal to 0. You could use a quadratic formula. I'm going to try to factor out a -16 that's in front of the t squared. Hopefully 144 is a multiple of 16, and it is. It is 9 times 16. We factor out a negative, so this is going to become negative. And then also 160 is. That's you get 16 times 10 gives you 160. Is this factorable? I think so. T minus 10 and t plus 1. All right, so this tells us that t is equal to 10 or t is equal to -1. We're going to ignore this t equals -1 because that is not applicable to our case. So we've got the time t equals 10 seconds. That's how long the rock takes to hit the ground. Hopefully nobody is down there because that'll probably hurt a lot, especially if it's a big rock. All right, so we want the velocity at this time. So let's plug in 1 into the velocity. So remember that the velocity function was negative 32t plus 144. Okay, so v of 1, oops, not v of 1, v of 10 is negative 32 times 10 plus 144. Okay, that comes out to be negative 176. Velocity's units are feet per second, if you're measured in feet and seconds. Okay, now here our velocity is negative, and that makes sense because the rock is going downward, when it hits the ground. So that is why it's negative. It's also pretty fast, right? 176, as opposed to the 122 up here. Of course, because as it falls, the longer it falls, the faster it will be going. Okay, part C asks us, find the maximum height that the rock reaches. That is not something we talked about before, but we have all the tools to figure this out. So based on your experience with the world, when you throw something up, it slows down and then it turns around and starts falling, right, back down to the ground. The point when gravity kind of overpowers the force from velocity, or from the initial upward trajectory of it, and then it turns around and goes downward again. So at that point when that happens, when the velocity changes from positive to negative, that's where the height will be the maximum. Okay, so in other words, the maximum height is going to occur when the rock kind of stops for just a second in the air and then starts to fall back down to the earth. In other words, that occurs when the velocity is equal to 0. Okay, so the max height occurs when velocity is equal to 0. Right, that's because when it's equal to 0, the velocity is changing from positive, going upward, to negative, going downward. And other places where the max height can happen. So if we set the velocity function, which is negative 32t plus 144, if we set that equal to 0, and we solve for t, I'm running out of space here, we will get 32t equals 144. We'll divide 144 by 32, and we get 4.5 seconds. Right, little t is a time. So 4.5 seconds into the toss is when the maximum height occurs, but we actually want what is the maximum height. So all we need to do is take this seconds and plug that into the height function. So this is the when. Now we need the actual height. Sorry, I'm always running out of a little space here. Virtual paper is great though, because you can just make things bigger or smaller. So let's put that over there. Okay, so now we want the height at this time. Okay, so we're going to plug in 4.5 into the height function. So that's negative 16 t squared. So negative 16, 4.5 squared, plus 144 times 4.5 plus 160. And let's see, so negative 16 times 4.5 squared, plug this into your calculator. And double check my calculator work. I do make calculator mistakes. It's so easy to do. I got 484. 484 feet. let's just check if this is reasonable. Our tower, we said, was 160 feet high. Is that reasonable for a building? I don't know. It seems a kind of, well, yeah, I guess so. We know that at 1 second it's 288 feet, but it's still going up because of its positive velocity. We know that in 10 seconds it's going to hit the ground. So about halfway, maybe it's at its peak. And at least its peak is higher than the building and what it was at 1 second. So, you know, comparatively to all the things that we were looking at, this does make sense. Okay, so at this point in your written homework number 4, I believe you can complete numbers 1 and 2. In the next few sections in this chapter, we will look at how to differentiate things that are equations and not just functions. I will let you wonder what that means, and I hope you have a wonderful week. Please come by office hours if you have any questions. I would really love to work on some homework with you. And if I don't see you, then I will hope again to see you in the following week.